Es ist jetzt 22:30 Uhr. Wir fangen jetzt an. Ihr seid im Vortrag From Oscar 1 to Mars and Beyond. And I switch to English because the talk will be in English. For a start, I have a few organizational points that I have to make. Please don't leave trash in here. Take your trash out. Supposedly, it has happened that a lot of trash has stayed in these rooms, and it's kind of bad if we have to clean it up ourselves. If you have something, please take it back. Please fill out or go into the web, into the wiki, and fill out the feedback form. If you like the talk, if you don't liked it, well, fill it out also. And then one very important point, on Sunday and on Monday, there will be no cars. I repeat, no cars allowed on the camp. So if you have to carry anything out of here, please organize carrying teams somehow. I'm just the relay, sorry. So when can I take a car to the camp? Yeah, obviously not on Sunday and Monday. That would leave Thursday, Tuesday, Wednesday, probably. But I'm not really informed. It's just that Sunday and Monday there will be no cars. If you have electronic waste, some of you happen to have some electronic devices probably, there's an e-storage behind the family village. Please don't drop the electronic waste in the normal dustbins or trash cans. Please bring them to the family village. All right. It's your last chance to fill up the lines in front. You have a much better view up here. If nobody wants to would. All right. This is the talk From Oscar 1 to Mars and Beyond. Let me introduce Mario Lorenz. He's from AMSAT DL. And he will talk about, he has somewhat about, I think, 70 satellites up in the orbits somewhere. And he will talk about what is complicated about shooting satellites up in the orbit, how to let them stay here. And, well, obviously for me, I don't know what is not complicated about building satellites. So please welcome Mario Lorenz, and it's your stage.
All right, thank you. Okay. Hello? First to introduce myself, my name is Mario Lorenz. I'm a ham radio amateur. My call sign is DL5MLO. And what that means is I'm, like many other of us, do not necessarily call ourselves hackers. But we as ham radio operators, we have been there years earlier than you. Nowadays, it's, oh, you are the computer guy, you can come and help fix my computer. Back then, in the times even before I've been born, was, oh, hey, you're the radio guy, can you come and help fix my TV? So there is much the same, much similar background. We also enjoy like playing with technology and do all the interesting stuff, except that we don't necessarily call ourselves hackers because, well, we've been there earlier and we've been given other nicknames. So, I'm a member of AMSAT DL. Obviously, I've been for quite some time, and actually I became more active in actually doing satellites in the aftermath of HAL 2001 in Holland. Maybe some of you have been there. So over there, we had the opportunity to do some satellite telemetry and did some interesting things, like just basically telemetry decoding of AO40. I'm going to tell you what AO40 is in a couple minutes. And well, obviously the press was there, and in some bigger computer publication, I later read that we were there hacking satellites and transforming them into mailboxes, which is obviously not entirely correct, but the idea. What I also did at HAL 2001 and the later things is I've been part of the power team. So I've been organizing or helping organizing later cables and so on, so that every one of you can have a good fun camp. Not here at this time. I'm only mentioning this because I want you to watch a little bit when I'm talking about power, because as you will see, this is somewhat important, and I will come back to this at the end of the lecture. So the outline of our talk, I'm going to present the history of amateur satellites. So this is in part a history talk. And while we go along that history, I'm gonna go a little bit in more detail on particular things on our satellites. So I'll highlight noteworthy things, and we are then going to look into what we're doing now, what we want to do, why and how we do it. And I'll wrap up with a little bit progress on, or summing up on this hackerspace program that's been here on the web, which was basically an idea why I came here and decided to maybe it would be nice if I could have this talk. Disclaimer, I have not actually built and sent to space any of these satellites myself. This has been our organization. I'm not long enough part of the organization to actually have done this myself, but nevertheless, I've learned quite a lot of how and what was done and what went wrong. I tried to get some of the more knowledgeable people and assign them the task of giving this talk here. But unfortunately, they couldn't make it. So maybe they're watching it on the stream. So any mistakes I make, it's your fault. All right. If you look at the history of satellites, you've seen a similar slide several times now. Satellites essentially started in 1957 with Sputnik 1. And this made Soviet Russia the first country to launch a satellite. Shortly after that, the first successful US satellite, Explorer 1 in '58. And then we are looking into 61, Yuri Gagarin as the first human in space. Now right there, Oscar 1 was launched. And Oscar 1 is the orbiting satellite carrying amateur radio. Is the first amateur radio satellite that was launched. So if you assume that our ham radio operators were some sort of a country, then we would have been the third quite unofficial country to actually launch a satellite, only 4 years after the first satellite, Sputnik 1, was launched. And quite earlier than some other countries who later launched their own satellites. So you can also add in here, Echo 1 is the first passive communication relay. It was basically just a big balloon in 1960 where you can just bounce off the signals as you can from the moon or any other things. And you can also add other Oscars that come in later that I will show a little bit in detail later. So now a little bit about our organization. As I said, Project Oscar, orbiting satellite carrying amateur radio. The first satellite, the program was started in '60, the successful launch in '61, as I already said. So in '69, it was decided that this needed a little bit more organization. So AMSAT North America was founded, which is basically the mother organization of all the AMSATs. As a non-profit organization, it's the Radio Amateur Satellite Corporation. In 1997, AMSAT DL was founded, which is basically the German counterpart of this, or the German, well, part of the family. In Marburg, in Marburg, basically close or located at the University of Marburg, ZDL, Zentrales Entwicklungslabor, which until even up today kind of serves as our gathering point where we actually built the satellite. So you would call it a hackerspace, but this is basically where our office is and where we do the German part of this. So the goals of AMSAT-DL are the advancement of science and research and development of satellites, including like testing these satellites in real space by the ham radio amateurs worldwide, giving them a platform to actually communicate. And of course, we also take research and education as important goals for young people and so on, just so that we have a continuing flow of engineers to help us put our satellites in orbit. Hello? You've been here before? Yeah. Satellites cost money, okay. That much is clear. I'm not going to give that much a talk on how to finance a satellite operation. There was a nice talk about how to do that, like selling sausages. This is obviously not really going to work. We are an all-volunteer organization that is like Hackers Everywhere. We do this for our personal enjoyment and our personal research. And the projects are financed by membership dues and donations from the industry. It's a big part. And of course, government grants for research, because we do like real research there. And yes, of course, this involves some paperwork, but if that's what's required to put a satellite in space, so be it. We launch as piggyback experimental flights, which makes things a little bit cheaper, but then again makes them a little bit more dangerous. AO40, which is the biggest of our satellites, had a budget of about 3 million euros. That's real money. Like if you look into all the donations and hardware that we got, it's probably way more. So let's look into the satellites again. We have here Sputnik 1. This is the first Russian satellite, and see what it did. It's a small, round, sphere of 56 centimeter. It had a weight of 83 kilograms, quite heavy, and it had two beacons on the HF bands with all the 4 antennas to actually transmit the signal, and so on. It had an orbital height of about 200 kilometers, slightly elliptical, up to 900 kilometers. It had a battery as a source of power, and this battery, of course, sometime it was flat, so after 21 days, there was no electricity, so the satellite shut down, and re-entry was after 92 days, so then it was off the orbit. So if you compare this to what we did with Oscar 1 only 4 years later, it was basically the same thing. We had a satellite, now this time in a higher frequency amateur band, which did nothing than send some basic Morse code telemetry, the high, which is nowadays kind of a tradition on AMSAT satellites to greet everyone with hi. Now, if you look at it, we've basically done the same, about 20 days of usable service life in about 300 kilometers of orbit, but we did it on 4.5 kilograms. So our satellites then already were smaller and, we could say, better, but well. Now, this satellite was launched, and this is an important point, with Discoverer 36. What does 36 mean? Obviously, it means the 36 rockets. So there have been plenty of rockets that have been sent to space back then, and now you can guess what they were for. The primary load of Discoverer 36 was a satellite of the type KH3, mosquitoes, which stands for keyhole. They were spy satellites by the military. And back then, the technology for spy satellites was analog. You have a satellite, you have a camera, you send that satellite up to space, you make pictures, and that film will then, or would then get sent down on Earth with a lander, where these pictures were collected, developed, so that you can look what the big bad guys on the other side of the Iron Curtain had in mind. Now, these 36 launches mean that you have to have some sort of industrialization. You have to launch them in series. And this is basically another kind of watchword or watch phrase that I wanted to give you, and that's cost of configuration change. When you launch a series of launchers, you don't if you know how to do it, you don't want to change anything. So if you have a different satellite, a lighter satellite in this case, you would fly ballast so that everything else, all your calculations, would come up to the same results. And this was basically the first of our launch opportunity back then. This ballast, when they said, okay, instead of using something useless that you shoot up there, they talked them into taking our first ham radio satellite up. Nowadays, it's not so easy anymore because usually there is not much ballast on these flights because they are basically sold out for each and everything for small satellites nowadays. So we are basically caught up by our own success. We've shown what we can do with small satellites. Now everyone built these, and now it's a business to send even small satellites up, which makes things, of course, more difficult for us. So in 1967, what we did, a balloon mission, basically to prove our linear transponder. A linear transponder basically is a piece of radio relay that takes a little bit frequency band, amplifies it, and sends it back. So you can talk about it. You can use any digital modes, whatever that was back then, usually CW, that is Morse code, or radio teletype. But it's basically transparent to the protocol. It's not intelligent about the protocol, so it can't do like regenerate the modulation, but it can amplify them and relay them. So you can basically do each and every and anything, and you can do it on a bandwidth here of, in this case, 80 kilohertz, which is several voice channels. So you have way more capacity than just a single voice relay or something like that. So that said, now history took its course over the years with all these satellites that we launched. I've already mentioned Oscar 1 in more detail, so I don't need to talk about this here anymore. Important is basically then here Oscar 3, Oscar 4, which were the first transponders that you actually could talk over the satellite to other radio amateurs. Also an important milestone is like here, Oscar 6, which is the first, we call them phase 2 satellites. As you can see over here, the operating day time was measured in days because they were powered by batteries. In some cases, they had some additional solar cells, but only here at Oscar 6, we reached a case where we actually had a power budget that was positive. So we were able to keep the satellite in space for 4.5 years. We then had Oscar 7. I'm going to talk about this a little bit more in more detail. That was up for 6 years in space. Then we had some other satellites. The Russians also had their own radio amateur satellites because, well, if the West is doing it, then of course the Russians, they couldn't be best, so they had to do it as well. And in 1980, we tried to launch our first satellite. Unfortunately, as we'll show later, we had a little problem there. So AMSAT Oscar 7 was the first satellite, basically one of the first satellites that were built by large international teams, and AMSAT Oscar 7 was the first satellite that we as AMSAT DL played a role in basically delivering the transponder payload. It's a special transponder HELAPS. It's for a high efficiency linear amplifier, which is basically an efficiency way better than anything else that's been on the market there. Well, unfortunately, this satellite fell silent after about 6 years in orbit due to a short circuit in the battery. So, of course, everyone thought, okay, well, happens. I mean, okay, 6 years is okay. Now, what happened in 2002? Suddenly, the satellite was back. Back in a way that obviously the short circuit opened back up. So, of course, we don't have any usable battery there anymore, but if the satellite is in sunlight and therefore has energy, and if some other things are about right, depends like in which mode it's in, this is like random, if it boots up, then it is usable. And I've heard the satellite just three or 4 days ago. So it is still there, and so therefore this is like the oldest still active satellite or amateur radio satellite that's in orbit and that's working. There's claims, I couldn't verify them, that this is in fact the oldest satellite of all of them that is still working. I mean, okay, if you got a couple of years of beauty sleep in the middle, that's not. So let's now get to P3A, which was the first big satellite as launched by AMSAT-DL. Was to be sent up on the second experimental launch of Ariane 1. The first or primary satellites were Firewheel, which is a German research satellite. We had a total mass of about 1,800 kilograms that were to be sent to GTO, which is the transfer orbit for a geostationary orbit. And again, here, this is our satellite as mounted on the launcher. It was to have a 50 watts linear transponder, a solid rocket engine to get our trajectory right, because the GTO orbit is an orbit that is especially designed to send up the satellites. You do a checkout there, and the orbit is not stable. So if your satellite doesn't work, which happens from time to time, the satellite will re-enter rather soon, and it does not take up the valuable geostationary orbit space where the commercial satellites all are. So all the satellites there have their own rocket engine, so they are sent to the GTO, checked out, and then they move on their own to their final destination. So we also on the satellite had our first freely programmable computer, IHU, based on a Cosmic 1802. This is one of the first microprocessors that were available in the 70s. Now, unfortunately, this is the image from the launch. It's about the last image of this rocket as it was alive. The whole rocket had a combustion instability and exploded shortly afterwards, and therefore leaving not too much left of our satellite. So that is, if you fly cheap on these cheap satellites or on these cheap missions, on these cheap operating systems, you always run the risk that something can go terribly wrong and years of work literally go up in flames. So this is the plan for a phase 3 orbit. It's a highly elliptical orbit where you have here about 36,000 kilometers on the apogee, so that you are quite far out, but you want the satellite to be that far out because the farther it out, the bigger is the footprint on Earth that you can talk. And since we are ham radio amateurs, we want to talk worldwide. We want to have a large footprint, therefore it's good if the satellite is far out. Of course, this also means that you have to take a high distance when you talk to the satellite, and that will then mean that you need quite a lot of power or quite big antennas to get there. It also means that you need quite a big amount of power on the satellite side, which makes these satellites like rather big compared to the CubeSats that are mainly flying in the low Earth orbit over here. So we've basically found a different sweet spot where we want to be. Instead of the low Earth orbit, we want to have these high-flying satellites because it gives us more communication capabilities. And there is another side effect. According to Kepler's laws on motion, the satellite is quite slow when it's in the apogee, where it's quite fast when it's close to Earth. If it's quite slow over here, that means we have a long time that we can talk. So the satellite is there for hours. Instead of if you have a low flying satellite, you have merely 5 to 10 usable minutes where you can have a short contact, but that's it. And there's many other people who also want to have a short contact. So these satellites tend to be quite crowded. So never give up. After P3A, we went on to do P3B, which is a basically similar satellite. About, again, a 50-watt linear transponder. Now, we have another transponder, this time for SHF, the L-band, because we even want to advance and want to move to higher frequency because we have more available bandwidth over there in these frequency ranges. So we can have more simultaneous contact possibilities. Wow. I should not. Well, if I go here, I'm blocking the. I just want to have you to want to have this nice view on these nice pictures that were taken. Okay. So again, here we had this Cosmec 1802 based computer that we have on the satellite to do our housekeeping. So look at what happened. We've just lost the satellite. We were quite under pressure to build the next one. And of course, we were financially strained. Financial strain means that you'll have to take interesting steps if you want to go to space. So this is one of our interesting steps. It's a helium pressure gas tank. This helium pressure gas tank stores helium, as the name implies, to get the propellants out for our rocket engine. Now, a space-rated, space-qualified tank is obviously very expensive, and we did not have the money for that. So what did we do? Like every other hacker would have done, we looked for something similar. In this case, this is an air tank, like it's used, for example, by firemen. We took it, we found out, okay, it doesn't have the required capabilities, but you can make it have these required capabilities by just strengthen it a little bit. So voila, here is a helium gas tank that has all the requirements, and therefore we can use as a tank and fly it at a fraction of the cost. Now, this is SAT IHU, internal housekeeping unit, which is controlling the satellite. This is the compute unit. This is the memory unit. You see that they are in aluminum casing and sometimes even have special shielding in here. As I said, it's based on the Cosmec 1802 radiation-hardened CPU. For some home computers, you had the non-radiation-hardened way, but then there were like people who had access to the radiation-hardened version, and somehow we got them. I mean, it's been said that these units, for example, have been used in ICBMs or other satellites. And we had 16 kilobytes of dynamic memory. We had to use this dynamic memory because we were promised to have radiation-hardened static memory, but that didn't work out. So on rather short notice, we just designed this one in. We knew that we would get into a radiation problem, and we got into a radiation problem. The high ecliptical orbits, they will have to fly through the Van Allen radiation belts like several times whenever they go around. So this accumulates quite some radiation. So finally, we succumbed, this unit succumbed to radiation about 3 years later. The operating system itself is also quite interesting. It's called IPS, Interactive Programming Language for Satellites. This is a Forth-like programming language, so like on a stack, we are programmed the way like Yoda talks. And it has it has had the capability that you can actually program this in space. We have a Forth interpreter on the satellite, and you therefore could update the program while in space, and this is an absolutely important capability to have. And why I'm gonna show you now. So we launched this successfully on LO6 launch in '83. However, after separation of the satellites in orbit, we got rammed by the upper stage. That means we had like deformed antennas, which we could prove by the radiation pattern. The satellite had a totally wrong orientation. In fact, it's been to a way that we didn't get much energy on the solar cells because to the sun, we were pointing with the part where we didn't have solar cells. The spin was in the wrong direction. Satellites are usually spun up for stabilization, and this was in the wrong direction. So all our sun sensors, which expected the sun to come up basically the other way around, did not work, so our stabilizing couldn't work. So what happened is basically in one night, we had to program a new firmware or new software to get this right, and we got it right. So we basically uploaded new code and could do it, and this capability to upload new software is therefore very important for us. As I said, the IHU succumbed to radiation damage in '86. The transponders still occasionally are working, but this is a rare event. Basically, we consider the satellite dead. Oscar 13 is basically also a similar story then, came in '88. Similar satellite, you've seen this before. Again, high power linear transponders. And now this time we were focusing for the first time on digital transponders. So we'd actually digital things to store and forward email, basically, in the ham radio thing. This time we did have radiation-hardened memory, so this time we didn't have a CPU problem. This satellite, we had basically a problem with the orbit due to some up to then unknown effects of the moon and the sun. The orbit kind of decayed, so we had a re-entry in, I think, '96. So this satellite, unfortunately, isn't there anymore. And then '91, we had Oscar 21, which was a payload on a Russian satellite, possible by the changed political climate. Again, mainly focusing on digital modes, but the problem with when flying on other satellites, they turned their satellite off on '94, and this cut us off from power, so this satellite also isn't usable anymore. And here's basically our then flagship project, Oscar 40, AO40, is the one that we heard back then at HAL 2001. It's the biggest, up to then, the biggest satellite, 650 kilograms, with many transponders, with a 400 Newton big engine, and we also had a small arcjet plasma engine that we intended to use for like station keeping. It flew quite a lot of interesting technologies. These are like momentum or reaction wheels for 3-axis stabilization, so that we then could point our antennas in the correct directions. They were like new even back then, and there are still few satellites that have them because there's something special on them. They are not like regular wheels. They have magnetic bearings, so they have like really little friction, so you can run them on way lower energy than anywhere else. We had other interesting experiments, for example, here a GPS receiver that we used to prove that you can have a GPS fix even when above the GPS orbits, where the satellites for the GPS system are, which was quite successful. And we had other interesting stuff, which I'm not going to go into much more detail. Well, what happened to this satellite? We had a malfunction during the main engine burn, unfortunately. So there must have been an explosion and a communications disruption, which can mean only one thing, that's trouble. But unfortunately, there were like backup procedures in there, like cycling around the different modes, different antennas to find a working combination. So a couple of days later, we were able to resurrect the satellite and could work over the satellite in a limited fashion until 2004, when again we had a short on the main battery, probably due to corrosion, because there was like dangerous stuff flowing around on that explosion. So we had like sagging voltage on the main bus. Command station was online and basically saw the satellite dying on its own hand. Said, okay, I might have been able to like try this, but unfortunately the voltage was already so low that a relay could not be turned to switch to an alternate battery. So we were basically unable to do anything, and this satellite died. So this left us without a satellite, unfortunately. So the idea is, where do we go next? There's already at this time, there were plenty of CubeSats showing up. So we decided, okay, we're not gonna do a CubeSat mission. We want, again, to build something flying higher to do like real communication. And so therefore, we look for a HEO orbit, or we even want to improve further. The main problem is, of course, how do you finance such a launch, because nobody's going to give you money just to build another amateur radio satellite. So we decided, okay, let's raise the stakes, let's go to Mars. As you see, the structure is like rather similar to what we've flown with AO40, and we've did some calculations. Yes, we can go to Mars if we have a couple other things ready. These other things that we've had ready, or that we'll have to have ready, is a communication link that will have to go all the way towards Mars and back, receiver, transmitter, and we have to have 24/7 experience in running this. Because now you're talking about antennas that you don't have in your home garden anymore. Of course, we need like things like a coherent transponder to ranging where we are. We need a new onboard computer, because now, the first time, we need like more power to do decoding for the channel codes for the long distance radio link. But we can like use pretty much the same satellite structure. We may need another qualification mission, preferably to Earth orbit, to high Earth orbit, where the conditions are closest to what we need when we go to Mars. And of course, we need launches. So working on this shopping list, we first found this old abandoned antenna dish in Bochum. It's got a 20-meter antenna in there, which is quite a big antenna. So like we polished it up, worked on the tracking, and we have now an antenna that's basically pointing more accurate than it did before, and does all the stuff that we want to do there. We put in a new transmitter in, then put in new receivers. And the first thing what we wanted to do is we want to show that we've got big ears. We can hear real faint signals. Faint signals in this case, the Voyager 1 spacecraft, at a distance of 14.7 billion kilometers. So here you see the happy guys of us who did it, and here you see the peak on the spectrum display. That is the signal coming from that distance. Now the next thing is, well, EME, you've seen the talk, making moon bounds, sending a signal up to moon and having it back, which is this is easy with a dish like this. So therefore we went a little bit further, and further in this case, we changed the M by a V. V stands for Venus. So Venus is another planet in this case. And we basically did the same thing that we do, or that they are still trying. I'm not sure whether they are successful. We may ask with the moon, basically use the moon as a relay. We've done this with Venus. Again, with our big amplifier that we put there, 5 kilowatts. And we send our traditional HI, high greeting, and a couple minutes later we got it back from Venus. So we now have proven that we actually can talk over interplanetary distances with the equipment that we have. Now we need 24-hour operating experience, and this is something where we can do something together with NASA. NASA has these two nice spacecraft here called stereo, A and B. A for ahead and B for behind. The mission of the spacecraft is to circle the sun, basically on Earth orbit. And the idea is that we have stereo A ahead of the Earth and B behind of the Earth to get 3D images of the sun. Now the problem with that was, back then, NASA had a little bit of a problem with unexpected long Mars missions. You've known about all the Mars rovers that were planned to be there just a couple weeks, that stayed there. I mean, they're still active. That was tying up the deep space network capacity for NASA. So what they did, they were asking other people to help them out, and we were just too glad to help them. They have a special beacon mode on the spacecraft where they send the current data, space weather data, that are received by a couple of volunteers. Again, like Bochum here, there's another station here in Kiel, and there are some other stations. This is Koganai in Japan. Toulouse is France, and this is Gibraltar in the UK, and this is like NASA Deep Space Network. So we try to provide a 24-hour coverage of this information, because if you observe the sun this time and you see something interesting happening, then they can schedule like immediate DSN time to look at this in detail and get the detailed data, but you need this trigger, and this can be very important because space weather is very important. Like if there is a explosion on the sun, this may impact like satellite or communications on Earth, and most of all, it also impacts like the people on the ISS. They may have to go to a safe compartment or like prepare for immediate departure just in case of problems. So it is rather important for us to be proud of this team. And again, it's something that's a mutual thing. So if we help NASA now, we hope that if we get into trouble, then maybe they will help us. So such a Mars mission is rather feasible even for amateurs. This is what we call a link budget. It basically says what kind of bit rate you can expect over that distance. And the important thing is we as a command station plan for the emergency case. Emergency case is the case where the satellite is tumbling, so the big antenna that you've seen here in front, that you still see here in front, is not pointing to Earth. We don't have high gain to Earth anymore. We only have the little omnidirectional antenna up here, which points to Earth. And we still need to talk to this, so we have this rather limited budget of communication speed of 5 bits per second downlink and 70 bits uplinks, which we hope will be sufficient to point this again into the right direction. Whereas if the antenna is pointing directly to Earth the way we want it, it means that even in your garden, if you want to put up a 2-meter dish, which is, well, okay, it's not your small dish anymore, but it's a manageable size, you can receive this basically on a direct link. And that's basically what we want to do so that you can basically receive your own signals from Mars. This is a picture of the IHU. This is the computer that we've been designing and working on. This is IHU 3. It's been designed basically together with AMSAT-NA, which is something that I need to mention here when I say we built the satellite. This is, of course, wrong. We as AMSAT-DL were the project coordinators for this specific satellite. We have contributions from all over the world, and this, of course, then means that also we contribute back to the other satellite organizations if they want to do their satellites. In total, we are up to like 70 satellites by now. This is originally a US project, the IHU, but unfortunately, after 9/11, the US people kind of got freaked out about like terrorists and this kind of stuff. So they tightened their ITAR export control things. So the AMSAT-NA people got into serious trouble for working on satellite projects over there. So we had like to take over, and we still hope that the situation may improve, that we can work together again, because if we work together, it's much easier to run these kind of huge projects. So what do you want to do if you have a satellite in Mars orbit? The idea is basically to be a communications relay for whatever needs that. May that be NASA missions, or may that be our own lander. We've been in contact with other people who said, okay, well, if you're going to Mars, then how about you take a Mars lander, and we'll do that lander, and so then we'll have something to talk to. So this is something that we want to do. But in the meantime, of course, when we have all the technology that we need to qualify that, and this is basically our P3E, again, a satellite to high Earth orbit with a main objective to test all the transponders and all this stuff, and allowing us radio amateurs to communicate with long visibility in areas where there actually are people to talk to, because if you spend much time here across the oceans, there's not too many people there. So this is AMSAT-DL. There's other AMSAT groups doing interesting stuff. AMSAT UK, they did something interesting that you may have heard about by now. This is the FunCube dongle. They built a CubeSat for small, well, basically as a satellite. And in order to enable reception by schools, they built this small receiver here. And this is basically a software-defined radio front-end in the size of this USB stick. I mean, this is a FunCube dongle here. And other than receiving the satellites that this was made for, we've seen other interesting things that you can listen to using this thing here at the camp. If you've, like yesterday, listened to the talk about Tetra. And at about 150 euros, it's quite a bargain. And again, this also helps putting the FunCube, which is the UK satellite, in space. So if you don't have one, get them. It's been quite difficult getting them because they were like produced by they were overwhelmed by the demand, the guy that was making them. So you had like big problems ordering them. And like he said, he was like, he was able to see what the processing limit of PayPal was. He sold like hundreds of these in a minute. And he said he could see in the PayPal processing that they limit you to about 3 transactions per second. Now, what I've did with actually this FunCube dongle, I hold the distance record of what can be received, 220 million kilometers. I used this to receive stereo B in Bochum earlier this year. Okay, I admit I cheated. I used this 20-meter dish and a down converter, but AMSAT-NA, the American people, they put a new satellite up just last week, delivered it via the ISS together with the Russians. You can see it, the satellite with the many names, ARISSat-1, also called Radioscaf V or Kether. It's a small, basically, satellite that they threw out of the ISS, literally. And what we did just 2 days, or actually 2 nights ago, here at the campus, we were like trying to receive the satellite. So we were like running around with these long, dangerous rods. If we were like a little bit grumpy when we were spoken to just the moment that the satellite comes up, the satellite only comes up every several hours. And that means there's just a small chance of working this. And when it comes over here at this time, it comes here overnight, so the satellite is not in sunlight. It's running on battery, so it's running on low power, energy saving mode. So during the path that we have, it would basically only send 1 or 2, or like 2.5 of these beacon blocks. So we were like really busy in getting this block, but ultimately I succeeded. So you see what the satellite is transmitting. Here you see it, hi, this is ARISSat-1. The hi, as I said, the traditional greeting. And here's like some telemetry that you see from there. So you see that obviously the solar panels don't give any voltage because we are in the shadow, that the satellite is quite warm. This was unexpected, and then there's some other data that we have here. So, wrapping up. There is this hackerspace program that has been posted to the web here, and that has been talked about like here at the opening session. And this is basically what was said that hackers or people need to do. So if you look at satellite communication, of course, we did that. Again, EME is boring. We did it with Venus. I hope this counts as well. A ground station network. I forgot to mention that. Yes, we do have several people working together on that. This was basically the idea about the satellites from the beginning, that ham radio amateurs worldwide would watch for these satellites and send in reports on how the telemetry was. So that's basically, yes, we do that as well. Satellite developments, okay, we with AMSAT-DL don't do so much with CubeSats, but other AMSAT organizations worldwide do. Long-range communication, I would think that 220 million or 16 billion qualifies as long-range communication. Technology development, again. Now, the first thing that we've not been into is the production of energy and power. And this is what I said. I want to come back shortly to that. This is something that you've seen when you looked at what the problems were with our satellites. Most of them finally ran out of battery or had problems with the battery. So what's really limiting us, even when we go here overnight, is the amount of power. So if hackers were to work on something, I suggest you work on the production or the harvesting of energy, and especially, and it's not on the hacker program so far, the storage of energy. Because if you have good storage of energy, this would help us in space, and it will also help here on the ground for the people like with wind and so on. Weather balloons, we've done as well. Moon rover, we haven't done, we are not too interested into this. Transport vehicles, we haven't done because, well, we are not there yet. Rocket science, yes, of course, we need a little bit of propulsion, and alternate spaceship propulsion, we've done as well. So that's where we stand. Quite a lot of the program has already been done so far. There's a couple open points that need to be tackled. So, thanks for your interest. If you got any any questions, you can ask them like here in just a second. I'm just finishing something up, or email me. I'm trying to help. Of course, we are also like always looking for volunteers at our organization. So if you want to help, also help us. We have a couple publications. The AMSA Journal, we are like kind of old-fashioned because old-fashioned things still do work. I have a couple of them here, so if you're interested, it's quite a few, so you're invited to have a look at them and take them. So that's it. And if you ever build your satellite, there's one last advice: try to keep it out of this book. This is the book about like space system failures. It's got plenty of things that went wrong, so you can learn a lot from this book. A couple of our satellites are unfortunately in there. The questions, it's been said, if you want to ask questions, please step up to the microphone.
Yeah, thank you, Mario. If you have any questions, step up to the microphone, queue up there, and we'll take them.
Okay. One question, the AMSAT Oscar 10, is it alive still?
As I said, we do not really count AO10 to be alive. Sometimes it's there, and I've heard reports just a couple of years or ago that it is still there. So it basically depends on the sign of the zodiac and other things that it's there.
Okay.
It may be there, but you can't rely on it.
What about propulsion? Do you use ion drives to lift the satellite to its orbit?
The propulsion to lift the satellites to the final orbit, like after they are in GTO, is basically what's been used in standard satellite things, because we got donated rocket engines from like Astrium and so on. So that's the standard liquid rocket propellant, which is hydrazine-based and an oxidizer.
No, think about ion drives. There are special vacuum tubes that are used to send ions out, so the satellite can use propulsion without using fuel.
Well, it's not, you always need a reaction mass, but we use that on AO40, which is basically you use lots of electricity to improve this reaction mass to make it faster. So I would like to go to, if that answers it, you can ask me again later. I would get to a little bit more people and give them a chance to ask the question, because I'm running a little bit low on time here.
Hi, I will have two questions, if I may. First, I would like to ask the crowd back then to be silent for a while. Yeah, so my first question would be, you were mentioning that the Oscar 7 had a short circuit in the battery.
Yep.
And I always wondered, like, how could you find out that it was the short circuit in the battery? Like, there was not so much telemetry, and also if you have some more probes always failing, they found out later. So I wonder, like, couldn't it be predicted? Or, like, what was the way they found out it's a short circuit on the battery? That's my question. First one.
Okay, essentially it's more or less simple. If you see the voltage of the satellite sacking down, you see you have a power problem. If there is nothing at all, like if there is no power there anymore, that means, or if you see that there was power from the solar cells, you can rule out that the solar cells are defective. And if there is nothing at all anymore from the battery, you know that it must be in the batteries. So if there is nothing there, the batteries are the obvious choice. If there was like the battery is just an open circuit, you would have the satellite while it's in sunlight powered from the solar cells. So it's a kind of like you deduce something from what you have in telemetry. You have like sensors of voltages, of currents, and then you can get an idea of what went wrong with the satellites. Of course, you never know for sure what exactly happened.
Yes, thank you. May I have the second question? Could you load up the slide, please, the one with the orbits you were mentioning? There was the orbit when...
I really don't want to go into these details. We can do it outside afterwards, if that's okay.
Okay, anyway, the question would be like, why they couldn't use the geosynchronous orbit back then? Why it needed to be a geostationary or whatever?
Our satellite isn't in a geostationary orbit. We hitched a ride for launch of a satellite to the geostationary orbit, and the intermediate end destination of your launcher is the GTO, the transfer orbit. And from there, the stationary satellites moved to the stationary orbit, and we moved to our orbit, which was a highly ecliptical one. I think last question. Last question?
Yeah, last question, please.
So I understand on your orbit how you want to have more coverage and more visibility.
Yep.
Have you considered the issues relating to receiver overload and like channel selectivity and stuff? Of how are you going to keep from having thousands of signals overloading your receiver when you can see all of the globe?
This has been actually a debate of research. This is why we flew like these linear transponders. This means that you have like, you can accommodate many people, and you have like problems with, you'd call them denial of service attacks, people using too much power. So we actually put in things that we call LILA, License Limit Anzeige, which would basically block out, notch out the people who are using too much power, and therefore not disturbing anyone else. So if you then reduced your power and work like and behave yourself, then you can work over the satellite. But we have protection measurements in place for this kind of, well, we call them crocodile attacks, like big mouth, small ear.
Okay, thank you.
Okay.
Thank you.
Okay, so again, you're invited. We got like a couple stickers. I'll be around, so if you're interested.
Okay, please thank the speaker again.